Yeah, that feeling, right? That constant background worry about your phone dying, or maybe bigger picture, how we actually get beyond fossil fuels, getting better energy storage, faster charging.
Right.
It's like this constant bottleneck we're all trying to figure out.
It really is. And that's why today we're doing a deep dive into some research that honestly could be a game changer for energy. We're looking at quantum batteries.
Quantum batteries, yeah. Specifically, there's this new paper on a minimal quantum battery model.
Exactly. The paper's called A Minimal Quantum Battery Model, Achieving the Quantum Speed Limit and Demonstrating Genuine Quantum Advantage. It's by Viraj Gajera and Dr. Noah Williams.
Okay, so our mission here is to unpack this. How does this simpler model actually work? Why is this such a big deal, this certified quantum advantage? And importantly, what could it mean for you listening, for your devices, maybe even bigger energy challenges?
Let's jump in.
Right. So maybe first, why even look at quantum stuff for batteries? What's the basic idea there?
Well, the promise comes from harnessing these kind of weird quantum phenomena, things like superposition and entanglement.
Right. Superposition, where something could be in multiple states at once, and entanglement, linking particles.
Exactly. For batteries, it means potentially using these quantum rules to charge and hold energy in ways that are just impossible classically. The aim is much better capacity and, crucially, much faster charging speeds.
Okay, but it hasn't been easy, right?
Yeah.
I remember reading about earlier quantum battery ideas facing some pretty big problems.
Oh, absolutely. Past models like there was the Sakhtyev-Kitaev battery, the SYK model. They tended to be incredibly complex.
Complicated how?
Well, they involved these very intricate systems, lots of entanglement, super hard to actually control or measure in a lab. And a big thing was many didn't have a clear, certified proof they were genuinely better than a classical battery. It was hard to pin down a real measurable quantum advantage.
Okay. And that leads us to this new paper, because it tackles those problems with apparently a much simpler approach. Why is simplicity such a win here?
It's huge because complexity was a major barrier. This new model is, almost surprisingly simple. It's basically just two coupled harmonic oscillators. You can think of one as the charger, the other as the battery.
Two oscillators.
Mm-hmm.
Okay. But simple doesn't always mean powerful. What's the trick?
The trick, or the key innovation, is what they call an anharmonic interaction that happens during the charging.
Anharmonic interaction. Okay, that sounds technical. What does it actually do?
Yeah, it's a bit of a mouthful, but think of it like this. Normally, energy transfer is like water flowing steadily. This anharmonic interaction, though, it acts like a kind of quantum shortcut. It enables what's called entanglement-assisted energy transfer.
A shortcut?
Yeah, a shortcut through the space of possibilities, Hilbert space, technically. It allows the energy to move much, much faster than it could classically. It's using quantum rules to bypass the usual speed limits.
So they didn't just theorize this shortcut. They actually showed it works and gives a real advantage. How do they, prove it?
Yes, and this is really the core finding. The model doesn't just hit the theoretical quantum speed limit, the absolute fastest possible energy transfer in quantum mechanics. It's also the first quantum battery model where this advantage is rigorously certified.
The first one? Wow.
Yeah, the first one proven using established methods, specifically bounds developed by Lowenstein and colleagues, to show it genuinely outperforms any classical equivalent. For you listening, that translates to potentially way faster charging and better efficiency than anything we have now.
That's pretty significant. And crucially, it's not just maths on a page. The paper says it's experimentally feasible.
Exactly. That's another key part. It's designed with real-world implementation in mind, suggesting it could work well with superconducting circuits.
The kind of tech already used in quantum computing research.
Precisely. So the building blocks, the know-how, it's sort of already there. This really opens the door to potentially building practical quantum energy storage devices down the line.
Okay, so let's just pull this together. We've got a quantum battery model. It's simple. It's proven to have a genuine quantum advantage, faster charging.
Yeah.
And it looks like it could actually be built. That feels like a real step forward.
It definitely is. And looking ahead, the next steps are pretty clear. Actually building and testing it experimentally, figuring out how to integrate it with other quantum tech, and then the really exciting part.
Which is?
Thinking about scaling it up, scaling the model for, potentially, macroscopic energy storage.
Macroscopic. Okay, so let's leave everyone with that thought. What could macroscopic quantum energy storage actually mean? For your life, for your